New Glenn just exploded, the launch pad is wrecked, and Blue Origin's lunar lander, just lost its only ride to space. Right now, there's only one name big enough to step in: Falcon Heavy, SpaceX, the direct competitor. Sounds like the perfect fix, right? But here's a detail almost nobody's talking about. Blue Moon runs on liquid hydrogen, a very particular propellant. It needs its own dedicated systems to pump and store. Falcon Heavy's pad? It's never serviced this propellant before. So the real question isn't which rocket is big enough, it's who builds that system and how long does it take? The answer could reshape the entire timeline NASA and Blue Origin are counting on. Let's dig in. Think of liquid hydrogen as the most demanding propellant out there. To keep it liquid, you need negative 253 degrees Celsius, colder than liquid oxygen, colder than the liquid methane Starship runs on. And because it's that cold, everything that touches it needs custom engineering, plumbing, valves, insulation, safety protocols. This isn't a small detail. Pad 39B at Kennedy Space Center, the pad that served Saturn V, then Space Shuttle, then SLS, took decades of construction and upgrades just to handle liquid hydrogen safely. Decades, not months. SpaceX's current launch infrastructure for Falcon 9 and Falcon Heavy is built around RP1, refined kerosene. Starship runs on methane. This next part is my own analysis, based on what's publicly known about SpaceX's infrastructure. Not a statement from NASA or SpaceX. If Falcon Heavy's pad in Florida has never handled hydrogen at scale, putting Blue Moon on it isn't just a swap on the launch schedule. It could be an entirely new infrastructure problem. But hold on. Before we go further, let's be clear on why Falcon Heavy is still the best option available, despite this issue. Because the rest of the bench is short. NASA's SLS already has its own Artemis schedule. No room to slot in another mission. ULA's Vulcan is grounded, pending an investigation into the BE-4 engine, the same engine that just caused the New Glenn explosion. Europe's Ariane 6 is still recovering from years of delays. So when Jared Isaacman, NASA's administrator, said in an interview that the agency is considering putting Blue Moon on a different launch vehicle, he didn't need to say Falcon Heavy. Process of elimination said it for him. Falcon Heavy is the best option, by size, by capability, by availability. The question isn't should they pick Falcon Heavy. It's, once they do, how much work stands between that decision and Blue Moon actually riding on top of it? And that's where the hydrogen problem comes back. Let's lay out 3 hypotheses. This is exactly how an engineer thinks through a problem that doesn't have a ready-made answer. Before we continue, if you're finding this breakdown useful, hit like so the channel knows you're following along. And if you haven't subscribed yet, now's a good time, because these 3 hypotheses are worth not missing. Hypothesis 1. Build an entirely new hydrogen system at SpaceX's pad. Picture this. Your house runs on an electric stove. Now you want to add a gas stove. You can't just buy the gas stove and set it down next to the electric one. You need dedicated gas lines, dedicated safety valves, dedicated ventilation. It's a completely separate project from the electrical system you already have. A hydrogen system for a rocket works the same way, but at industrial scale, with a much higher safety margin. Because this isn't cooking gas. This is a propellant that can explode if it leaks. If NASA and SpaceX go this route, a full build from scratch, based on how comparable systems have been built historically in this industry, this is likely a multi-year project, not months. And if that's the case, we run into a pretty ironic paradox. Falcon Heavy gets mentioned because it's fast, available, already flying, no waiting required. But if fast only applies to the rocket itself, while the ground infrastructure needs years to prepare, the real total timeline might not be much faster than Blue Origin simply repairing their own LC-36. This isn't to say Falcon Heavy is the wrong choice. It's to say the best choice on paper and the fastest choice in reality can be 2 very different stories. Hypothesis 2, and this is the angle almost nobody's raised. Redesign Blue Moon Mark I for a different propellant, specifically methane. Just switch the fuel, right? But this isn't like pouring different gas into a car that already has a fuel tank. The propellant a spacecraft runs on determines almost everything about its design. Tank size. Hydrogen needs much bigger tanks than methane, due to its lower density. Center of gravity, where those bigger tanks sit, affects how the vehicle flies and lands. And engine architecture, hydrogen-burning engines and methane-burning engines are mechanically different structures. In other words, this isn't swapping fuel. This is redesigning nearly the entire vehicle on a spacecraft that's already nearly finished. So why bring up this hypothesis at all? Because if you zoom out past a single mission, this could be the highest long-term value path. A methane-powered blue moon would be far more compatible with the infrastructure SpaceX has already built for Starship, not just for Falcon Heavy, for any future launch option. But there's a timeline problem. Isaacman has been clear. NASA wants Blue Moon ready for the Artemis 3 test mission in 2027, with a possible landing target in 2028. If redesigning the engine and propellant systems is necessary, the question becomes, can that process realistically finish in time for those milestones? This is the most radical of the three hypotheses. The long-term payoff could be huge, but so is the schedule risk.
Hypothesis 3, and in my view, possibly the most realistic, a small-scale temporary ground solution.
Not every hydrogen system needs to be the size of Pad 39B. Historically, in this industry, engineering teams have built mobile or semi-permanent fueling systems, sufficient for one or two specific launches, without constructing an entire permanent large-scale facility. Think of it this way. You don't need to build a whole new gas station if you just need to fuel one car, one time. You can bring in a mobile fuel truck, fill up on-site, and move on. If this is the direction, a hydrogen fueling setup, sized just for the Blue Moon Mark 1 mission, the prep timeline could be significantly shorter than Hypothesis 1. And this is also the hypothesis that best fits how Isaacman phrased things. He didn't say, we're rebuilding the entire launch system. He said NASA is considering other launch vehicles. Considering is a careful word. It signals this is still in the evaluation phase, not a final decision, not yet a project with an approved budget and a locked timeline. Now, let's step back. There's an interesting comparison point here that I think deserves attention. Starship, the human landing system variant for Artemis, also doesn't run on hydrogen. It runs on methane, which means across the entire Artemis program, NASA is working with two landers running on two completely different propellants. One hydrogen, Blue Moon. One methane, Starship HLS. This isn't anyone's mistake. It's the result of NASA selecting multiple independent contractors, each designing what they consider the optimal solution. But it also means NASA's ground infrastructure ecosystem, over time, has to support multiple propellants at once, not just one. And that's exactly why Falcon Heavy carrying Blue Moon becomes a systemic question, not just a question about one flight. If NASA and SpaceX solve the hydrogen problem this time, through any of the three hypotheses we just covered, it's not just a solution for Blue Moon Mark 1. It could become the precedent for any future hydrogen lander that needs a backup launch vehicle. On the flip side, if this problem turns out to be too complex, too time-consuming, that's a lesson too. A lesson that when companies design landers and rockets independently, without building in cross-compatibility from day one, the cost of a forced swap later can be enormous. So, putting it all together, what are we actually looking at here? We're looking at a decision that seems simple on the surface. Which rocket is big enough to carry Blue Moon? Answer, Falcon Heavy. Done. But underneath that simple answer is a completely different layer of problems. Propellant chemistry, ground infrastructure, the gap between a decision that's correct on paper and one that's correct in practice, and how much time separates the two. This is a familiar pattern in aerospace. The right strategic call isn't always the fastest one to execute. The two get conflated in early headlines, because Falcon Heavy can carry Blue Moon is an easy, clean headline. But Falcon Heavy can carry Blue Moon, by which month? That's a question only time and specific engineering decisions from NASA and SpaceX in the coming months can answer. There's one more thing about hydrogen worth mentioning. Not about construction, but day-to-day operations. If you followed SLS launches, you've probably heard the word scrub, a last-minute launch cancellation, come up a lot. One of the most common causes? Hydrogen leaks at the connection point between the pad and the rocket. This isn't because NASA's engineers are doing a poor job. It's because of hydrogen's nature. It's the smallest molecule there is. capable of slipping through gaps that no other propellant can. A rubber seal worn down by a fraction of a millimeter. For RP1 or methane, that might not matter. For hydrogen, that can scrub an entire launch attempt. So how does this connect to the Falcon Heavy story? If, and I want to stress, this is still an if, SpaceX has to build a brand new hydrogen fueling system. That's not just a build it once and you're done problem. It's also a system SpaceX has zero operational experience with. And in aerospace, the gap between built and operating smoothly and reliably is usually measured in real-world test cycles, not in blueprints. This is also why, even under Hypothesis 3, the small-scale temporary system, there's still reliability risk on the first few fueling attempts. Not because the design is flawed, but because it's the first time a specific team is operating a specific system with a propellant they're not yet used to. And looking at it from the positive side, this is exactly why every time a new company learns to handle hydrogen, it's a step forward for the entire industry, not just for SpaceX or just for Blue Origin, for anyone in the future who has to work with the most demanding propellant in spaceflight. None of this gives you a guaranteed answer right now, but it gives you the right questions to ask every time new Falcon Heavy Blue Moon news drops in the coming months. When NASA makes its next announcement, pay attention to whether they're talking about the rocket or about the ground fueling systems. That distinction, small as it sounds, will tell you a lot about the real timeline playing out behind closed doors at NASA and SpaceX. And one more small detail. But if you catch it, it might be the earliest signal of which hypothesis NASA is leaning toward. Watch for whether, in upcoming statements, anyone, even in passing, uses phrases like ground systems or fueling infrastructure. Because if NASA starts talking about reassessing ground systems in Florida, instead of just talking about which rocket will fly, that's the clearest sign yet that the hydrogen problem we just walked through isn't just a hypothesis anymore. This hydrogen question doesn't have an answer yet, but now you know exactly where to look. Thanks for following along. If you found this useful, like, share, drop your thoughts in the comments, and subscribe to the Space Brief. Another video is waiting on your screen right now.